very confining pressure in a sequence of experiments you find something like this. So basically, we're talking about taking several cylinders of rock, applying different combinations of sigma 1 and sigma 3 to them until they break. We can plot that on the Moore diagram. So this would be, let's do one experiment. So we start out, maybe we start out with sigma 1 and 3 equal, then we decrease sigma 3, and it breaks at a certain point. And we can plot that, what that Moore circle looks like at the moment that the fracture occurred. We can even measure the angle relative to sigma 1 that the fracture occurred at and mark it on there. And then we could do another experiment. Get a new cylinder of rock, maybe do it at a higher sigma 3. So let's say that this one broke at sigma 3 there. Let's do another experiment with sigma 3 is here. Increase sigma 1 until it breaks. Turns out it plots something like that. Bigger differential stress at the higher confining pressure. And then we do another one, even higher. Looks something like that. And if we plot those fractures, they tend to be at about that position. So we can define this surface here, basically that would go through these x's and intersect the circles. And that surface is what we call a fracture envelope. It's also known as the fracture criterion. And one of the things it's telling us is that as confining pressure increases, the shear stress on the fractures that form needs to get higher and higher in order for motion to occur, or for fracturing to occur. And one thing we can say about the orientation there, usually fractures are 25 to 35 degrees to sigma 1. Depends somewhat on rock type. It's never 45, which is a little bit puzzling. If you think about the Moore circle shows us that at theta equals 45, that would be, for any given Moore circle, maximum shear stress is at that point when that angle theta is, or 2 theta is 90 degrees. So it is the shear stress on those surfaces that's going to cause them to actually fracture. So you'd think maybe that when the shear stress was the largest, that's when the fracture would occur. But instead, it tends to be off to the side there. And so basically, the way we can understand that is this point has, just because of the shape of the circle, basically, both of those have a very similar shear stress. But there's a significant reduction in normal stress from that point to that point. So it turns out that, you can imagine, as one of the things that the Mohr circle is telling us, if you're going to try to have, break a fracture on some surface, it's easiest to do it when you're not pushing very hard together, when the normal stress is pretty small. So we can basically apply almost the same shear stress in the situation if we're over here, but significantly decrease the normal stress. So that's why these fractures are occurring sort of not at the maximum shear stress, but still pretty high. And this plot in this surface here, the fracture envelope, gives us a way of predicting when rocks are going to fail. So if we're digging, one of the exercises in the lab on Friday will be to basically to predict, the size of a pillar that would be needed in a mine in order to hold up the roof of the mine without having that pillar actually fracture. So the surface tells us that. So if we were like, okay, the overburden is, the weight pushing down is over here, what's the area of that, what's that would keep that circle safely, away from the point where you're going to have fracture. And we'll talk more about that, and we can go over questions on this lecture in the lab on Friday.